Hello and welcome to our Capstone project presentation on our variable air volume control apparatus for the HVAC undergraduate laboratory. My name is Christina McCusker and my teammates are Emily Albano and Ava Struby.
So we'll begin this presentation with a little bit of background on the project. So in 2018, the Faculty of Engineering and the ASHRAE Regina chapter partnered together to create the first heating, ventilation, air conditioning, and refrigeration course and complementary laboratory. So ever since then, the instructors have been looking to expand the laboratory component through the use of additional equipment. Currently, the lab only has one piece of equipment, which is the closed-loop hydronic heating apparatus. And so as undergraduate students, we understand that commercial lab equipment is very expensive. And so we wanted to be able to bridge this gap for the future students by providing students with an educational piece of interactive equipment that would show lab exercises such as energy balancing, a runaway condition, as well as automated and manual control, as well as giving future students an overall appreciation of HVAC systems. Moving on to the objectives, the first being to design and build an interactive teaching apparatus that demonstrates the fundamentals of air movement, heat transfer, and building control. Along with this, it will demonstrate the use of variable air volume units and the fan coil to cool 3 unique environments of fluctuating temperatures, just as we would see in a real-world scenario. With this, we've also created a lab manual, which includes a schematic of the apparatus, lab exercises to enhance student learning, as well as information on building control principles. So our project features 2 main components, the first being the variable air volume boxes. These boxes are used to control the volume of air that flows into the miniature rooms, and they work by using a temperature input and digital control that relays information from the rooms back to a small damper located inside of the unit. So on the top right-hand corner here, we can see this image where you can actually see the damper inside of the unit. So when more air is needed, that damper will open, and when less air is needed, it will close. The second component is the fan coil. So for our application, the fan coil is used to represent an air handling unit that you would normally find in a commercial building. Air handling units work by taking ambient air from the outside, cleaning the air by passing it through a filter, heating or cooling the air, and then forcing it back through the building ductwork. The fan coil will provide ambient air from the lab space to the variable air volume units at a constant pressure.
So once we had established the objectives and basic components of our equipment, we moved forward with the engineering design process to begin designing our equipment. We first started with some basic system requirements. These included physical constraints. So since we wanted the apparatus to be portable throughout the university, it needed to be small enough to fit through doors and hallways, as well as into elevators. We also needed to be aware of what sort of power we would have access to in the lab room and make sure that any power requirements on our equipment was compatible with the lab space. In terms of design constraints, in keeping with our learning objectives, we wanted all processes to be as visible as possible for students. This meant keeping the cooling process slow enough to be observable, being able to demonstrate a variety of tasks on the equipment, and making sure that all of the pieces of equipment were visible. This meant building at an accessible height and keeping the equipment spaced out enough to be seen. Finally, as we were students working with external funding, we needed to keep budget in mind at all times, not only to keep our costs low, but to make sure that we were meeting the different requirements for the grants and funding that we would be receiving. After establishing those requirements, we moved forward with a more specific system design. In this stage, we used an iterative Excel spreadsheet to determine the number of unique zones we wanted, the heat requirements for those zones, and the airflow requirements for the system as a whole. For this spreadsheet, we used a modified version of the heat transfer equation as seen on the slide. This equation uses the heat source values from each of the miniature rooms, as well as the temperature difference between the supply air and the desired temperature of the miniature rooms. It then calculates the airflow requirements for the cooling process. Using this method made it easy to determine the minimum and maximum airflow requirements of our system, allowing us to accurately size our equipment. While looking into equipment sizing, we found that many variable air volume boxes have minimum airflow requirements to ensure their accuracy. To make sure we met these minimum requirements while still not cooling our rooms too quickly, we used the spreadsheet to design bleed-offs into the system. These bleed-offs allowed us to supply the appropriate amount of air through the variable air volume boxes and expel this air into the lab room before they reach our miniature zones. Once we had sized our equipment, we moved forward with equipment selection. We decided to go with Price Industries as our equipment supplier, as they have a good reputation when working with student groups, and we really valued the support that they could offer us for this project. To select our equipment, we started by looking at the performance information available in the specification sheets and making some preliminary selections. We were then able to meet with a price product engineer who gave us some further advice and let us know how our equipment selections would work in our applications. Once we were confident in our selections, we placed an order for the equipment with price. Some other selections that needed to be made included the base structure design and materials, the ductwork sizing, the heat sources, and our viewing ports. To size our ductwork, we used the maximum airflow requirements calculated from the spreadsheet, as well as static pressure information to determine how big the ducts needed to be, while still not going over our maximum size capacities. For our heat sources, we knew we wanted them to be small enough to fit into our miniature rooms, easily adjustable, and easy to determine their heat output. For these reasons, we selected 150-watt incandescent light bulbs on dimmer switches as our heat sources. Finally, for our viewing ports, as we wanted all processes to be as visible as possible for students, we decided to integrate acrylic windows into the miniature rooms, the variable air volume boxes, and the main stretch of ductwork.
Continuing on with the engineering design process, we used a weighted decision matrix to evaluate 3 of our preliminary designs. The matrix has the categories of size, portability, and cost, which come from our initial design constraints, as well as aesthetics, performance, feasibility of construction, equipment visibility, and safety. Each category was given a weight based on its relative importance to the project, and each design was scored in each category. Design 1, which can be seen on this slide here, has 3 benches with airflow control box room systems and a 4th bench with the fan coil mounted in the back. Each of these benches hits the portability constraints, as it can be fit through doorways and into elevators. However, for the design to be fully portable, the ductwork would have to be removed and reattached every time that the design was moved. It also offers great visibility of all the processes with plenty of space for students to see, but it takes up a lot of space in the laboratory, which was a consideration moving forward as the laboratory is trying to expand and add more equipment year to year. In design 2, the entire design is contained in one apparatus, with the fan coil mounted on the bottom, the airflow control boxes in the middle, and the miniature rooms on top. This easily hits those size and portability constraints, as it can fit through doorways and in elevators. However, the visibility is lacking, particularly the middle airflow control box would be very hard for students to see the inner workings of the airflow control box. It also could have a performance suffer, as there's a lack of a straight line of ductwork into the inlet of the airflow control boxes, which was a recommendation based on the specification sheets of the airflow control boxes, that there be a minimum of 12 inches of straight ductwork into the inlet for optimum performance. So this could cause the performance to suffer. In design 3, the fan coil is again mounted on the bottom, and each subsequent shelf has an airflow control box room system. This offers great visibility of all 3 systems simultaneously, while still meeting those size and portability constraints. It also has ample room for that straight line of ductwork into the inlet of the airflow control boxes, so the performance would not suffer in this design. As you can see, design 3 earned the highest score and had no major weaknesses. We decided to move forward with design 3 for our final design. Quickly to touch on the components of the design. First, on the bottom is the fan coil, which pulls in ambient air from the laboratory and pushes it through the ductwork. After the fan coil, an electric duct heater is installed in the ductwork. This is discussed a little bit later in the laboratory exercises section. After that, the air is pushed into the 3 systems. Each shelf has a manual balancing damper for manual control of the system. After that, it moves through the airflow control boxes. After the airflow control boxes, the ductwork splits into 2 streams. One stream goes directly to the environment. As Emily mentioned, this just gives us greater flexibility of the system and allows us to control the amount of air into the room to a higher degree than the airflow control boxes are capable on their own. The rest of the air goes into the miniature rooms, and each of the miniature rooms is equipped with a heat source in the form of a 150-watt light bulb, as well as a thermostat, which is wired back to the airflow control boxes. After we finalized our design, we designed a cart to be able to safely and effectively hold all of our equipment. For the material, we used a mild steel based on a recommendation from our workshop technician, and backed up this decision with a finite element analysis. We also included cross bracing on the bottom of the bench, where a majority of the weight from the fan coil would be held. Finally, we finished the entire apparatus with a powder coating in order to prevent rust, improve aesthetics, and ensure long-term operation.
So we also just want to take a brief moment to touch on the safety of the project. So for this, our team approached safety from two different perspectives. The first being within the actual design features of the apparatus. So making sure that we limited physical access to hot surfaces inside of the room through the use of remote controlled thermostats, as well as just making sure that the design itself was clean and contained. The second is through the communication and implementation within the laboratory. So we made sure that in the lab manual, we've outlined all of the applicable laboratory rules and any additional rules that might be relevant to the apparatus. So now that we had the cart design, the system design, and the equipment ordered, it was time to move on to the assembly process. So here, our team was able to demonstrate our project management skills through the following steps. Beginning with an initial consultation, we met with the team at Christie Mechanical to discuss the construction of this apparatus. So we chose Christie Mechanical since they are a local company here in Regina, and we knew that they'd be able to provide continuous support throughout the lifetime of the project. This first meeting just allowed for some open discussion on the actual logistics of the construction, as well as addressing any concerns or design changes that might need to happen ahead of time. Moving on, we finalized the design. This was an important step just to make sure that both our team and the team at Christie Mechanical had the same understanding of the expected outcomes, as well as making sure that any errors due to miscommunication would be avoided. The following weeks consisted of any design changes or requests for information and approvals from Christie Mechanical as anything came up throughout the design. Once everything was actually assembled on the apparatus, it was time to move on to the controls. So for this, our team met with the controls engineer at Price Industries, and he was able to walk us through the complex setup and testing of the controls. And then finally, that brought us to the final fabrication of the apparatus, which was completed back in February.
So after we completed that final fabrication, we were able to move into testing and verification of our design and equipment. In this stage, we used the manual air balancing dampers as well as the integrated control system to isolate each of the components to ensure they were operating as expected. This stage also allowed us to verify the safety of the equipment before implementation. After that verification was complete, we were able to move forward with implementation into the laboratory. This was a pretty unique situation as we were actually introducing this equipment into a lab that we are all currently enrolled in as students. One way that the equipment can be operated within the lab is through the integrated control system. This system operates on a private network server, allowing for secure access for all students within the lab. Through this control system, students can set temperature set points in the miniature rooms, as well as airflow targets for the variable air volume boxes. This system also allows students to see a graphical representation of the operation of the equipment.
We created a lab manual to include with the equipment for use in the course. So the lab manual includes a description, a schematic, a safety section, some operation instructions, as well as some potential exercises. The exercises that we developed demonstrate three main concepts. The first being automatic control. So the system can be set to regulate the temperature automatically based on the set point temperatures in the miniature rooms. Students can then observe how the airflow control boxes try to balance the system. And this simulates how a real building control system using variable air volume control would operate. In the manual control exercise, the airflow control boxes can be deactivated and students can attempt to manually balance the system using the manual balancing dampers installed in the ductwork. This will allow students to gain an appreciation for how complex building control systems actually are, as they will fail miserably overshooting the system trying to hit those set point temperatures. In the last exercise, the electric duct heater will be powered on without the student's knowledge. This will cause the supply air to be warm instead of that ambient air temperature coming from the laboratory, and will cause the rooms to get warmer and warmer instead of cooling as they're supposed to. This causes a runaway condition. Students can then try to troubleshoot the system to figure out what's happening, and this allows them to gain a greater understanding for the system as a whole and how it works.
So as we mentioned earlier, the budget was a large constraint on the project since we are undergraduate students and any funding we would be receiving was limited to what we could get from academic grants. So just to start, we made some initial cost estimates. This was done, number one, to be able to communicate with those academic grants where the money would be allocated. And number two, to act as a guideline for us throughout the project when it came down to ordering equipment. We then have a cost breakdown. Here on the left-hand side, we have a table showing the actual material value of each of the components and labor. So we broke this down into the stand, the equipment, which includes the variable air volume units and the fan coil, labor and assembly cost, powder coating of the stand, controls, and then accessories such as the light bulbs and light fixtures. We should also note that we had a generous donation from Price Industries on both the equipment and the controls. And then on the right-hand side here, we just have a pie chart showing the allocation of each of those material costs, not accounting for the donations. We can then compare our final model against two different models from GU and T Hamburg. These are two models that are available to the university for purchase. So the first being the ET620, which is the air conditioning ventilation system. And then we also have the ET915, which is the refrigeration and air conditioning system. So from the bar chart here, we can see that there are significant cost savings with our design. And then just to summarize, the total value of our apparatus came out to $21,983. And then once we applied the grant money that we received, it comes out as no cost to the university.
So moving forward with this project, the overall big picture goal is for our equipment to be integrated into a larger system of lab equipment. Last year, a similar Capstone group developed a hydronic heating apparatus. Next year, a refrigeration cycle apparatus will be created, and in the following year, a building control system will be designed to help tie all three systems together. Our group helped to facilitate this big picture goal by making very specific design choices. This included selecting a fan coil with heating and cooling coils, which will allow for easy connections to the hydronic heating and refrigeration cycles, as well as a control system that is robust enough to support more than just the system on it right now.
That concludes our presentation. Here you can see a picture of our completed lab equipment in the laboratory. We would also like to thank all the people who made this project possible. First, our industry supervisors, Brad Lulick and Jared Larson from McPherson Engineering. Our faculty supervisor, Dr. Adesorn Arun-Wheelas at the University of Regina. Chris Young from the University of Regina Machine Shop. Mike Malden and Mike Thompson from Price Industries. And Ryan McLean and his team from Christie Mechanical. We also want to thank APEGS and AFRE for the grants and funding we received to pursue this project. Thank you, and we have a short video that highlights our components.